Our next talk is by Michal Koucky, who will talk on his journey with Earth. Thank you.
Well, thanks for the invitation actually to speak, and this is a great opportunity, and I'm a bit actually just let's see how it goes. So so actually you can look actually here, and this is a picture which is you may be guessing how old it is. So it's like almost 20 years ago actually. So okay, so I'm going to talk about actually some parts of Eric's work which we didn't hear much about. So I'm not going to mention the K word here. And so I'm going to talk about, I think, a passion which we both share with Eric, and that's Turing machines and circuits. So let me just start by Turing machines. So when I say Turing machine, I actually think the device like this, and I hope everyone knows what Turing machine is. And we can think of different variants, based either like deterministic or non-deterministic or probabilistic. And I will actually first talk about non-deterministic ones. So when we are talking of non-deterministic Turing machines or non-deterministic computation, we usually think of this computation tree. So you got your input X, and somehow the machine starts to compute, and there are like these divergent paths of the computation that we think of. And usually when we want to say that the machine accepts, then we have these accepting nodes, and at least one of the nodes has to be accepting for the input to be accepted. And of course, there is a big open problem actually. If I give you a language which is not recognized by a non-deterministic machine, can we actually recognize it by what we call common deterministic machines, or can we actually flip the acceptance conditions? So so is there a machine? So for each machine M, if it's running, say, in polynomial time, so we measure the time by the length of the computation. And for each language in NP, is there, we know that X is in L if and only if there is some accepting computation on that input. And we would like to be some other machine M prime here, which would also run in polynomial time, and it will have the opposite property. So if X is in the language, there is no accepting computation. And of course, that's a big open problem. It's still open. We don't know actually what's the outcome. But you can formulate actually a bunch of other similar questions actually about accepting computations. And one of them actually, which is kind of resolved, is actually so-called unambiguous computation. So that was resolved by Valiant. And here, what the goal is actually, I got a machine M which has the usual like NP condition, and I want to actually modify it into a machine which actually has exactly one unique path. So if there originally was like multiple accepting paths, now I want to have just like single acceptance paths. And this is the famous Valiant-Vazirani result on isolation, and they actually show that basically there is a reduction from NP to basically kind of like UP. So I kind of like put there quotation marks. It may not be exactly correct, but let's take it. So that's basically what they show. And how you can think of it, actually, you can think of it, what they really have is they have a transformation which takes a formula psi and maps it to some formula psi prime, so that if the original formula was satisfiable, then now we have unique satisfying assignment. If the formula was unsatisfiable, it's still unsatisfiable. So that's what they actually did, and this reduction was randomized, and they actually produced like a bunch of possibilities, and one of them actually has this problem. So that's actually NP. But you can actually so this was time-bounded actually computation. So when you actually restrict the time, but it's actually fairly natural to also restrict space. And then we could talk about like NP space, but usually what people focus on is actually small complexity classes like NL. So in the class NL, you have again like the computation or deterministic computation, and you want to accept it, but each computation actually runs in tiny space, in logarithmic space. So that's what I mean by log space. And probably you all heard about this amazing theorem of Immermann and Selepseny from '87, which actually says that actually does the stuff which we wanted to do for NP, and CoNP, it does it for actually NL. So it actually establishes that NL is equal to NL. And it's done by this beautiful technique of inductive counting. And when this came up, actually, people were trying to apply this to various things, and they managed to put like SL into CoSL and things like that. But that's pretty much what they were like able to do. So around this time, up until actually here is so what does it actually mean? What does it mean? Well, you can take actually what the result actually of MMM selection, and what it actually does is that they have like efficient reduction of connectivity problem where you are given a graph and you are given two vertices and you want to know whether there is a path. And the yes instances are the ones where there is a path. So they have an efficient reduction which actually turns it around. So you get some graph G prime and S prime T prime, and there is a path between S and T if and only if there is a path between S prime T prime. So that's kind of like mind-boggling how we can actually do that, but they actually managed. And people try to do more stuff, but as I said, they pushed a little bit, but but basically up until results of Eric and Reinhardt, actually they didn't like do the real thing, and I think this was the real thing. So the real thing was that Eric Reinhardt actually showed that NL is in UL/poly. So that's a very nice result, and yeah. So that's and here is Eric actually showing where there is actually NL. So that's actually below P.
Does this inclusion apply changes?
Well, one thing. So it's actually the reduction is actually again slightly randomized. So you need a little bit of non-determinism for that. So actually, like you need some random advice, and I don't think actually it implies it. So not even like in some bigger sense. That's one thing. The other thing is that yeah, you could actually de-randomize this one. So you can actually de-randomize it as opposed to say Valiant Vazirani. Well, that could also be perhaps de-randomized, but this one can be de-randomized under, I would say, standard assumptions. And also the result actually is kind of able to detect wrong advice. So if you feed it wrong advice, it actually kind of tells you.
If you combine the two, you get something like UL is contained in co-UL/poly.
Yeah.
But is it known whether UL equals co-UL?
Well, I just say no, so I will take a sword for that. Okay, so that's actually a really beautiful result. And if you haven't read the paper, I encourage you to really read it. So what does it do? Basically, well, in terms of graphs, again, like it takes a graph which has like perhaps multiple paths from S to T, and it turns it into a graph which has just single paths. And if there was no path, then there is no path. So that's actually what the reduction does. Okay, so that's kind of Turing machines, non-deterministic Turing machines. So let's go back to the computation tree, and let's actually just be looking and staring at the tree a little bit. And people actually stared at this, and they actually generalized the notion of non-determinism, and they generalized it to alternating computation. So far, basically, we have seen deterministic and non-deterministic, non-deterministic computation that you can kind of like mix and match. So like alternating computation, basically, like whenever you kind of are flipping a coin, this non-deterministic coin, you can decide basically like kind of like the acceptance condition. So whether both paths, the way you flip, actually should be accepting, or whether like just at least one of them suffices. So if the existential means basically like at least one of the paths should be accepting, and which actually means the subtree should be accepting, and the for all means actually both the branches should be accepting. And that's how you basically define alternating computation. And you can like have there like in your computation tree, you can have like various states, and the states in the Turing machines are basically labeled whether they are like these existential or universal. So non-deterministic computation corresponds to completely basically existential. Universal corresponds to non-deterministic. Okay, so this kind of looks like a circuit, and indeed, actually, Rousseau in '80s actually basically postulated that this corresponds to like circuits. So you can actually tweak alternating machines and basically make out of them circuits, where what in some sense you get like from the universal quantifiers you get AND gates, and from these guys from existential you get actually OR gates, and it's kind of like a one-to-one correspondence. And people in '80s actually were looking at it, and they also noticed that it actually kind of works higher up. So if you look on polynomial hierarchy, then you kind of get like exponential size AC0 circuits. So that was kind of known. And then there was this, like another like surprising theorem by Toda. Which basically puts like whole polynomial hierarchy, basically kind of massages into a computation, which I think roughly looks like this. So you have this polynomial hierarchy where we are just like have some fixed number of layers, alternating layers between existential and universal quantifier, and then you can turn it into a computation which is like a BPP at the top, and then you have these parity quantifiers. So the parity quantifier is satisfied if like the number of accepting passes is odd. Otherwise, it's not satisfied. BPP like operator is satisfied if like the majority of the passes is accepting, like strict majority. So that's basically what Toda did in '89, and I think that inspired actually Eric, or at least he says that in his paper, that actually you can put like AC0 with parity into actually quasi-polynomial depth to circuit of this form. So you have like here the parity, and here are the AND gates. So that's actually Eric's result from '89, and it actually really again uses this duality between circuits and alternating computation. So it's kind of like taking advantage of that. Of course, also it involves Strasbourg-Smolensky, so that's kind of like how you would go about it. And right, so this is what we have. It's a probabilistic circuit, so you can actually make it into deterministic by actually replacing the gauge by majority. So you can actually make it into threshold depth-3 circuit of quasi-polynomial size. So that was in '89, and oops, that should have been Eric. I don't know. He disappeared. So now this was actually then extended by Yao, and by Beagle and Tarwe. So they actually extended it to whole ACC0. So ACC0 allows you to do ANDs, ORs, mod M gates for fixed M, and you can actually transform any such circuit into a circuit which is depth 2 circuit. You get like at the top you get a symmetric gate. So symmetric means that it just depends on the number of inputs that are set to 1. And then at the bottom, you have these AND gates, which are kind of like fairly small, so they have like polylogarithmic fanning. And so I actually, I think, made this non-uniform, and then the Beagle-Tauri actually made it uniform. And again, actually, so Eric actually took advantage of this. So that's actually another beautiful result of Eric. So in '94, he actually proved that permanent doesn't have uniform ACC0 circuits of sub-exponential size. So that's permanent. That's this sharp P-complete problem, computing a permanent of matrix. And again, like the proof actually really uses this duality between the two concepts, actually between the computation tree and the circuits, actually in a very crucial way. And you can see Eric is really happy about the result, actually. And that was actually followed by Eric by yet another result, actually in '99. And he actually pushes this from ACC0 to TC0. So TC0 are majority gates and constant depths. And that seems to be like stronger class, actually. And but the bound actually he gets is weaker, let's say like super like quasi-polynomial. So permanent doesn't have polynomial size circuit in TC0. So then, yeah.
What is the uniformity condition?
So I would say it's like the standard uniformity, D-log time uniformity, actually. So this means actually uniform result. So I will kind of like back, how does it compare to what we know? But let me actually just like, because that's probably running through your head. So how does it compare to Ryan? So Ryan in 2013-14, so he proved this breakthrough result that Next doesn't have ACC0 circuits of exponential size or sub-exponential size. And so how does it compare? So Ryan has a bigger class Next, so that's presumably a harder problem than permanent. So permanent is sitting in P space, so that's perhaps which is in X. So Next is even bigger than that. But the difference is really like Ryan's result actually works for non-uniform circuits, whereas Eric's works only for uniform. And we don't know how to actually extend the result to TC0. So that's so this gap between ACC0 and TC0 seems to be, at least with respect to our techniques, actually big. So Eric is still happy,
But is the parity immediate in the TC0?
Yeah, parity is immediately in TC0.
So why was the previous result by Allender ACC0 parity is inside TC0?
That's actually okay. So maybe let me just go back. So the point is that this is a depth reduction. This reduces the depth of the circuit to 3 layers. So you take arbitrary kind of like fixed depth circuit and you squash it into depth.
Oh, it's the 3. Yeah, sure.
Otherwise, it would be like 0.
Yeah.
Thanks. Okay, so this duality between actually circuits and acceptance trees actually serves as basically like it's helpful to prove level bounds. So kind of like to appreciate more these, let's actually a little bit dig into these small circuit classes, or like this area around these small circuit or small space programs. So we know that permanent is sharply complete, so perhaps it's like a fairly complex problem, and the best upper bound I guess we have is like P space, and determinant that's on the other hand. So you just want to compute determinant of a matrix. So we both everyone knows that these are like totally different problems computationally, but it turns out that determinant is really easy even in terms of space. So you can actually do space in really small space. You can actually compute determinant, and yeah. So it's sitting in a class which is so-called sharp L. So that's the number of accepting computations of log space Turing machine. It's technically speaking, it's actually difference of 2 functions like that. So it's like in gap L. But think of it basically like sharp L. And then sharp L, if you actually look on this class, if you are not used to it, you may not know where it actually sits in this circuit hierarchy, but it actually sits very low. So it's in NC3. So
I think it's NC2.
Yeah, okay, maybe NC2. I will get there. So NCI, that's just binary ends and or nodes, and polynomial size log I, log to the I depth. So this would be log to the C depth. So right. So let me just give you like simple argument at least that like log space is sitting in NC2. And well, you just we have seen that the complete problem for non-deterministic log space is actually graph connectivity. And if you take a adjacency matrix and you want to compute its transitive closure, you can like multiply the matrix 1 by 1. So basically like multiplying 2 matrices over Boolean summering, that can be done like in NC1. That's a trivial exercise. If you want to actually compute connectivity, then you just make a tree of these multiplications of logarithmic depths, and that's going to give you NC2. So NC2 is really like encapsulating these small space classes, and that's why actually this determinant is actually very low in the complexity. And if we compare it back to what Eric showed, and he actually is showing that this ACC0 and TC0 doesn't actually contain determinant, but all these actually things are also uniform. So there is actually something. So he's actually saying something really like surprising. So what do we know about small depth circuits? So of course, like we know that ACC0 is contained in TC0. We know TC0 is in C1, but it's still open whether these classes actually somehow are the same, whether they collapse. So, for example, we don't know whether permanent is in uniform NC3. So that's kind of open, and that would be, I would say, shocking actually, because it would mean that it's computable in log cube space. So, but we are unable to prove it. We know that the determinant is there, but we aren't able to prove it about permanent. So how can we actually go about like proving these things? Well, here is a result which we have with Eric. So it turns out that you don't have to prove like crazy super polynomial Laver bands actually to prove this. The only thing you have to prove is that basically, majority is not computable ACC0 circuits of size n to the 1 plus epsilon. So in particular, what we prove is that if majority is computable ACC0 circuits of some polynomial size, then it's actually computable by circuits of size n to the 1 plus epsilon. And you can actually make similar argument for TC0 with respect to some NC1 complete problems like formula evaluation. And so if you can actually prove this n to the 1 plus epsilon bounds, Laver bounds on ACC0 or TC0 circuits, then you basically won. So I think this kind of like fed then into this stream of magnification. We call it like that. But actually, what was actually surprising to me, like I guess like 3 or 4 years back, actually, Vijay and Roy actually showed kind of improvement on this result. And what they showed is that this epsilon can be replaced basically like 1 over C to the D. So like really like you need like barely actually super linear actually Laver bands. So the D is the depth of the circuit. So over here, this epsilon actually dependent on the depth of the circuit, and the bigger the circuit, then the better Laver band you would have to prove, like 1 over D. But over here, they got actually exponentially. And this is actually really close to Laver bands which people know how to prove, for example, for parity. So this is actually not completely far-fetched that we could prove those Laver bands. So how about arithmetic functions? So so we have seen that kind of determinant is in small space, and so let's look on other functions which are kind of basic. So like addition and summation, that's an easier exercise to do it in AC0. And then what next you could do. So what do I mean by addition? You just get 2 inputs, x and y, both of n bit strings, and you want to output this n+1 summation or subtraction. So that's nice. So how about multiplication? Well, actually, multiplication allows you to do parity, because that's an easy exercise. So you cannot put it in AC0. So you have to go outside, but if you go to TC0, then you get like multiplication like very easy. And then how about division? Well, division. So division actually is also in TC0, and that was actually known since 80s. But Eric with Dave Barrington and William Hess, they actually proved that actually the circuits can be actually made completely uniform. And this is actually very nice. This came out about the time when there was this Pentium bug, or maybe the Pentium bug was like slightly after, when they actually had the problem with division. And it turns out that actually really like the circuitry we have in our computers actually use some non-trivial algorithms to the division. So indeed, I think this is, it may well be that like one day actually Eric's algorithm is going to run our computers.
It reminds me that around the same time there were dubious claims about the GCD problem. What's the current status of the GCD problem?
I think it's still wide open.
There were claims at the time.
I know.
It's wide open to do anything better.
Like in NC.
Anything better than N, anything better than.
We don't know if
N
it's-
over poly.
Yeah, I mean, it's certainly polytime computable. We don't know any kind of parallel.
Yeah, anything better than N over poly law.
Something like
With
that.
sugar.
And the approach that was suggested is completely flawed even at the heuristic level, or it's just that, are there any informed conjectures, like that approach that was proposed is flawed even as a heuristic?
The approach that was in that paper by Vito is dead, but, you know, it's a problem. You look at it. And there's this Russo and, I think Russo and Tampa had a paper where they, that's fine. Anyway, we can talk about this another time.
So actually, yeah, let me just point out, actually, this kind of came after Little's paper. I think there was also some back actually there. And so like mentioning a little bit.
It's true, David, a little, right?
Sorry again?
Was it true, David, a little? Yeah.
The question is that it's not conjecture given that that is in TC0. It's conjecture that that is like the class of Koucky, right? It's between NC2 and NC1.
Right. So can you actually disprove this? Yeah.
Oh, disprove.
You know, so that's kind of like that goes back to this permanent thing, you know, like so proof any of these ladder bounds or like put it there. So that's the So we have seen actually like two techniques how to build actually a circuit from Turing machines. One of them was actually looking on this tree actually of alternating computation, and the other one was actually this NC2 where we actually upper bounded the size of log space actually. And there is yet another way you probably actually all know, and that's Pippinger-Fisher result that if you have d time Tn. Turing machine computation, then you can actually turn it into a circuit of size Tn log Tn and depth Tn. And you know, like usually, what I do is I teach actually weak result that you can actually do Tn kind of Tn squared, where you take this Cook-Levin basically tableau where each line actually corresponds to line of the computations. Just let's think of one tape and then every four tapes in this kind of configuration, like ABC implies what B is, so you can easily like replace it by a circuit, and that gives you a circuit of size T squared. And of course, so that's kind of like well lazy. Actually, only recently I found out that actually that Pippinger and Fisher actually had like a really simple construction. So this is the picture of their construction actually. Which gives you this Tn log Tn, and you know, so there is actually a lot of questions you can ask about this construction. It's a inductive construction where you basically go from circuit Cm, which kind of makes m steps of computation, into circuit C2m, which makes 2m steps of the computation, and it's just based on a like very simple observation that if you know where the head is, then you can shift it so that the circuit Cm would have it in a kind of reasonable position, and then you just so basically you are just shifting and right, exactly. It's also used there, and this result is kind of at the very end of the paper, and nobody reads that. So. Right. Well, yeah, except for I am here. So basically, so it's actually really easy, and you should learn it, and you should actually teach it. And so this rotation can be done by a linear size device, so you end up with actually linear size. You end up with circuits of size m log m, which actually kind of make m steps of computation. So you get this depth Tn log Tn. Now the question is, what do you get something better if you have actually unbounded circuits? So if you have unbounded finite circuits, then you can actually reduce the depth a little bit while maintaining the size. So you can actually do like Tn over log Tn while keeping the size Tn log Tn. And you know, if you go to size Tn to the 1 plus epsilon, then you can actually you can actually do depths like Tn over log n. So you can actually slightly reduce the depths if you have unbounded Fedin gates. So of course, there is a big question to me, which I have found really fascinating, and that's actually, can you do better actually for simulation of Turing machines? And I think this is like great unsolved mystery. And maybe it's actually hard in the general like multi-tape model. But how about if you have just single-tape Turing machine? I mean, there ought to be something simpler actually, like something smaller. And you know, I would encourage young people to actually think about this problem, because it seems to be nice. So I'm nearing the end of my talk. So let me actually just like push one problem which I really like, and that's probably like all CS people should like, because that's sorting. So in the sorting problem, you probably know zillions of algorithms, but you get like n integers, and each integer is actually 2 log n bits each. And maybe you know this n log n lower bound. So let me just tell you that's complete crap, because that's actually linear lower bound, because the input has size n log n. So I don't know any superlinear lower bound. And if you go to Turing machines, you can sort in time n log square n. If you go to circuits, you can sort in size n log square n, and that's basically like NC1 or something close to that. And can you do better actually? And well, I think that this is really like kind of like a ripe to prove lower bounds for. And I'm kind of, I tried, but I didn't succeed. But I would, you know, it's a really nice problem. Why is it actually a nice problem? Because you have, it's a multi-output function. So as opposed to just Boolean function, it's actually where you know, it's just like you have one bit of output and it's hard to argue about it. This actually gives you like m inputs you know, m output, so it's actually much harder function just by definition. And yeah.
So one way to do this is
Proof?
maybe overkill. Is to get to what you claim, not to improve it. Is there's like a linear size log depth comparator network, and then you could replace each comparator with log size.
Right, but that gives you exactly the size.
So is all that needed to get that and log squared? If you just do something more.
Right, yeah, good. Actually, you can do that, and you get like n square, the depth log square or something, or maybe a little bit less, but yeah. Good. So that's for the upper bound, but for the lower bound, actually, the lower bound would not actually break any natural assumption. You know, you can really like use whatever techniques you like, because it's really like modest lower bound. So I think this would like even like for NC1 circuits, actually proving such lower bound is not known. So let me finish here. So Eric is dancing away.
Are there any questions?
Let's do occasion.
Is that waltz or what is that?
This is English dancing.
The occasion is Tuesday.
The occasion is a special English country dance ball.
Oh, okay.
Yeah, Eric is known for actually his dancing interest.
Yeah.
Can you prove this lower bound under an assumption like network coding?
Yes, actually, that's a good question. So under network coding, you actually can prove this assumption. I suspect this should probably be also true. I didn't actually think about it actually. So you can actually prove it under some assumptions. Actually, people try to prove like superlinear lower bounds on Turing machines, like already like in 70s.
What is network coding?
Oh, network coding. That's network coding is this problem when you want to transmit like information from multiple sources to multiple destinations, and you have like a network where there are capacities on the edges, and but like in the individual nodes you can do various computations. So there is this standard example which kind of breaks the intuition that you know you want to transmit two bits, like one bit A from towards here, one bit here, and your network looks like this. So you want to basically like cross these nodes, and like with a normal flow, it would be impossible. But if you actually consider information, you just like send here A plus B, and over here you send B, and over here you send A, and you recover the thing. So the network code, so this is called network coding, and network coding conjecture basically says that you cannot do much better than like network flow on undirected graphs.
And you can simulate sorting algorithms with network coding?
No, but the network coding, basically like what the network coding is useful for, actually like this conjecture, the network coding conjecture postulates that this example is kind of like not happening under normal circumstances. So under that conjecture, basically like the computation just has to follow normal rules, and you can actually argue, about the information flow, actually. Ask about the flow.
The first one, like TM, is that on like a one tape, one head model where we have like lower bounds?
No, if you have one tape, then you can prove that you need like square.
That's great. Okay.
So it's two tapes.
What about median? Median?
I'll have to see the movie. It's probably like on one tape you can prove that it requires like one square.
I mean, median is no harder than sorting, right?
Right, on one tape.
On one tape. No, but I'm asking what's the status in terms of
For median. Yeah, I don't know actually.
Well, for median, for binary inputs, it's just majority.
Right,
And
but for non-binary. Is it easier than sorting?
One.
Thanks again.